Okay, kids, so we're back, section 4.1. We're going to talk about work. And work is a concept that we studied in grade 11. So we're going to do a quick review here. Work is done on an object when a force is applied to that object through a displacement. And when this work is done on an object by a force, energy is transferred to that object. So the whole idea here in this big wordy thing I wrote can be all encapsulated in one of the more important equations that we learned in grade 11. That when work is done, energy is transferred. Now, sometimes we do a calculation and the answer of work and energy transfer is negative. That means the object that had work done on it by a particular force has lost energy in that situation due to that force. Sometimes it's zero, doesn't gain or lose energy, but sometimes a force is applied to an object and that force does work on that object and it gives that object energy. So there's been a gain. Those are the three main ways of looking at this equation that we did look at in grade 11. Next, so we've got our Cartesian plane here, drawn x hat, y hat. Here's an object and a force is acting on that object. And while this force is acting on this object here is going to move. It's going to start from here, and a little bit later it'll be right there. And while it underwent this displacement, this force was applied on it. And in grade 11, we learned that the way to calculate this force, which is constant, this force doesn't change, the way to calculate this work is we take the force and then we do a special type of multiplication, F dot delta D, force dot product displacement. So this D is known as the dot product. It's also known as the scalar product, and we use this in grade 11. And the way we work out this calculation is right here. We take the magnitude of the force, so we take the magnitude of the force vector right there, take the magnitude of that, take the magnitude of the displacement vector, and we multiply that product of these magnitudes by the cosine of the angle between these two vectors, the force vector and the displacement vector, when they are drawn with their tails together there. And this is all stuff that we learned in grade 11. So I think the best thing to do here right now is let's go through an example to get us uh, refamiliarized, I should say, that's the word, with uh, the concept of work being done on an object and therefore energy being transferred. So here's a situation that we have. A brush is pushed with a force of 5 newtons 30 degrees below the horizontal for positive 0.20 meters x hat. The brush undergoes uniform motion. That means constant velocity. Acceleration is zero. It's not speeding up. It's not slowing down. So we're going to use that equation that we learned in grade 11, and I just reviewed it for you. But before we do that, let's draw a free body diagram. That's always important when we look at forces doing work. And one of the forces is 30 degrees below the horizontal. So if we superimpose an x hat, y hat plane on this, it'll help us see where these forces are. Now the first one is 30 degrees below the horizontal. So that is the work done by the applied force right there, and it's 30 degrees right there. What other forces would be acting on this? Well, you got to remember that there's the force of gravity acting on this object while it's being pushed. This brush is being pushed, it's on the earth. So there's a force of gravity acting on the object. What else is acting on the object? Well, there's a normal force. What else is acting on the object? Well, there's the force of kinetic friction. So we've drawn the free body diagram. And now Now what we're going to do is try to calculate the work done by the applied force, the work done by the force of gravity, the work done by the normal force, the work done by the force of kinetic friction. And what equation are we going to use to calculate that? We're going to use the free body diagram, our given information, and this dot product equation, which expands into this. So this was actually something that was given to you in grade 11, but it's been a while. So I'm going to suggest you try this, pause the video, try it, and then come back to the video and we'll see how this question should have been solved. So pause the video right now and try it for yourself. When you're done, come back. Okay, welcome back. So the first thing we're going to do is calculate the work done by the applied force, which would be force applied dot the displacement that the object underwent, and that turns into the magnitude of the applied force times the magnitude of the displacement times the cosine of the angle between them. Now remember, we've got a displacement here, and we've got a force applied here, and we're told that it's 30 degrees here between them for theta. So here we're going to put in the magnitude of the 5 Newton force, which is at 30 degrees. Here we're going to put in the magnitude of positive 2.0 meters x hat, and here we're going to put in the cosine of 30 degrees. So the magnitude of 5 newtons at 30 degrees just becomes 5 newtons. The magnitude of positive 2 meters x hat just becomes positive 2 meters. And this becomes cosine of 30 degrees. And when we put this into our handy dandy fancy dancy calculator, we get 8.7 newtons times meters. But hopefully you remember from grade 11 that a newton meter, or the unit for energy, the unit for work, is the joule. So there's your first one. I hope that's what you got for that one. I really do. Next, how about the work done by the force of gravity, which would equal force of gravity dot the displacement, which is the magnitude of the force of gravity, the magnitude of the displacement, times the cosine of the angle between the force of gravity and displacement. Well, here's your displacement. Here's your force of gravity. That's 90 degrees. So this becomes magnitude of the force of gravity, magnitude of the displacement. Oh, my computer slowed down there. What's going on? Magnitude of displacement, and then the cosine of 90 degrees. Well, last time I checked, kids, the cosine of 90 degrees, is 0. So you got a 0 in here. 0 times anything is 0. Work done by the force of gravity is 0. Similarly, the normal force, right? Here's the displacement. Here's the normal force. Oh my goodness, it's 90 degrees in there. So similarly, the work done by the normal force is 0 joules. 0 joules. All right, what about the work done by the force of kinetic friction? The work done by the force of kinetic friction. Well, we always start with this. And this would be the magnitude of the force of kinetic friction, the magnitude of the displacement, and the cosine of the angle between them. So let's draw this here. Let's see, you would have the force of kinetic friction pointing that way, while the displacement is pointing this way. It's all in the x hat. lo and behold, this angle right in here is they're 180 degrees apart. They're pointing in opposite directions. That's kind of cool. So, don't know what this is yet, so I'm just going to write it. This is the magnitude of that positive 2 meters x hat. And this is the cosine of 180 degrees. So this becomes the magnitude of the force of kinetic friction. This just becomes 2 meters. We just want the magnitude. And this becomes, well, the cosine of 180 degrees is -1. But I still don't know what the force of kinetic friction is, so I have to do a little bit more work. So let's take a look at the free body diagram again. We have the normal force, the force of gravity, the force of kinetic friction, and at an angle of 30 degrees is that force applied, okay? So if we take a look at this, we've got to remember here that the acceleration of this object is 0. Acceleration is 0. That means acceleration x component is 0, acceleration y component is 0. It's all 0 here. And if we write down F net, x component is going to equal the mass of the object times acceleration x component, which we know that's 0. But F net x component, well, the only forces that are acting in the x component are force of kinetic friction and force applied x component. So it brings us back to something we learned a long time ago, that when you have these types of forces, you got to break them down into components. Force applied x component there and force applied y component there. So we're bringing back some memories here. And this is going to equal 0. Why? Well, because acceleration in the x direction is 0. So that means I can take force applied x component, right? Bring it to the other side, make it negative. So I brought this to the other side, make it negative. And I've got force of kinetic friction is equal to the negative of force applied x component, which I can use right here. So in here, I'm going to put minus force applied x component times 2 times -1. All right. Now, what is force applied x component? Well, it's force, right? There's my 30 degrees in here. That x component is is adjacent to the 30 degrees. So this becomes force applied cosine 30 degrees times 2 meters times -1. So you've got to remember that you've got to break these forces down into components if this is going to work for you, right? These forces have to be broken down into components because with that one force applied not being totally in X, not being totally in Y, that's the only way around it. And the reason I bring this up and I'm taking so long to talk about it is, um, it just shows you how important components are in everything we do, So I'm going to leave you to calculate that. I hope you get -4.3 newtons times 2 meters times -1. So this becomes 4.3 newtons because all we want is the magnitude. This still is 2 meters times -1. And we get, I've done some rounding there. It's about 8.6, 8.7 newtons, but it's a negative sign. I think I may have rounded that off too much. So it's in that ballpark for sure. So I may have rounded this one off just a little bit wrong. So we're going to go with negative 8.7 newtons. So if we take a look here, we can calculate something called the net work, right? Just like we had net force, we add up the work done by the applied force, the work done by gravity, the work done by the normal force, the work done by the force of kinetic friction. So this one here is your positive 8.7 newtons, plus 0 newtons, plus 0 newtons, and then minus 8.7 newtons. So the net work is actually, oh, look at that, I've been so silly. Those aren't newtons, those are joules. Let me fix that. I made a big boo-boo there. That's okay. I make boo-boos too. Okay, we're going to fix that right now. Joules, 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 and joules. So overall, the net work is 0. Gravity and normal force don't do any work. Whatever work is put in, whatever energy is transferred by the applied force, the kinetic friction force takes it right out. Takes it right out. And you could have actually figured this out another way. Work net is equal to F net dot delta D. But since the object had no acceleration, net force is actually 0 newtons, right? Dot delta D, which will give you 0 joules again. Either way you look at it. Either way you look at it. Now, another thing we want to look at is calculating how much work is done by graphing. Okay? And the graphs that you use are graphing these quantities. So here, you would graph the magnitude of the displacement, and over here you would have the magnitude of the force you're interested in evaluating times the cosine of the angle between that force and the displacement. Now, if you have a constant force, your graph here will look like this. Now, how am I going to get work? What am I going to do to this graph to calculate work? Well, what you do is you simply calculate the area of the graph you made. So if the object was experiencing this constant force for, I don't know, 1, 2, 3, 4, let's say for 5 meters. So for 5 meters worth of displacement, this object was experiencing this force. What you do is you calculate the area. You calculate the area. And remember, when we calculate area here, it's length times width because it's rectangular, right? The area here would be equal to length times width. Well, what's the length? Well, the length is along here, right? It's along this axis, so it would be so many joules. So we would represent that by this. And what are we going to multiply that by? Well, by how much displacement you had, right there. Well, look, we've got our old equation again. It's just in a slightly different order. It's exactly the same as this. Just change the order. So by calculating this area, you have indeed calculated the work done. You have calculated the work done. But what about this situation? Now, we don't see a lot of this in high school physics, but I'm going to show you anyways. It is only briefly mentioned. What about if you're graphing whatever the object that you're applying a force to, it undergoes a certain amount of displacement, right? And over here, you're going to take a look at the force cos theta that is applied to that object as being pushed. But let's say as you push the object, right, as someone pushes the object, the force increases, right? You don't usually do a lot of this in our level of physics. This is a changing force. Okay, this is a changing force. So as the object experiences displacement, the force on it gets bigger and bigger and bigger. But let's say you wanted to calculate how much work was done by that force. Well, we're going to steal an idea from here. You can still do that. You calculate the area under this graph. If it works here, it'll work there, right? So you're going to calculate the area under the graph. That'll be the work, right? So here, area is equal to the base, delta D, times the height of the triangle, so whatever value it would have up there, all over 2. And if you did that, you'd be calculating the work. So let's say, oh, it got pushed for 5 meters. Oh, and where did the force max out at? Oh, it maxed out at 10 newtons, right? Well, that's what you would put in there. Divide by 2, and you would have your work. Now, if you really want to get fancy schmancy, right, and this is more like a university situation, let's say you had your force cos theta here on this axis again, and here you had your delta D. But now we had a parabola in here, right? So let's say the object went through a displacement, and here's where it ends, right there. That's as far as the displacement gets. So the force only operates over this displacement. And you still wanted to calculate how much work it was done. But this force increases not linearly. This force increases as a quadratic. It's a parabola. How would you calculate what work was done? Well, we're going to steal an idea from up there. Yeah, you guessed it. Calculate this area. Well, how do you calculate the area under there? It's not a rectangle. It's not a triangle. How would I go about doing that? Well, that's calculus. And you're going to have to wait to learn how to do that. You're just scratching the surface, kids. Okay? Have a great day. Bye-bye.